Alright, kiddos, we're going to do vodcast 2.1. We're going to talk about phase change calculations. So remember everything that's led up till now. We talked about kinetic theory in the last vodcast. And if you remember where we left off in the last vodcast was basically we had this diagram where we've got increasing kinetic energy going along the side. And remember that kinetic energy is basically temperature for us. And then from that, we've got solid, liquid, and gas. So as we increase the kinetic energy, we change the phase. We go from solid to liquid to gas. And then remember that we pointed out that there are these barriers basically between solid and liquid and between liquid and gas. They're called phase boundaries, and later on in the year we'll talk about phase diagrams and we'll see a little bit more of that. But those are basically there. And that's an amount of energy that's required to do that actual change from solid to liquid in this case and from liquid to gas in this case. Those barriers have a specific name. They're called heat of fusion and heat of vaporization. We'll take some notes on them in a little bit and talk about what the number values that are associated with each of those are. Also remember that when we left off the last podcast, we had this little diagram where we're talking about the differences in phases, so make sure that you know the name for each phase change, whether it's from solid to gas or gas back to solid, the reverse reaction. Make sure that you know each of those, what they are. That'll be important as we do these calculations coming up. So the first of those is evaporation, and basically what's going on in evaporation is that the particles of a liquid are escaping the surface of the liquid and they're turning into gas phase. And so if we look at our diagrams here, okay, so we look at this first diagram, and what we got going on here is that you've got particles here at the surface of the liquid that have enough energy and they're going to escape into gas phase. So how does that work? Well, if you remember back to the Boltzmann diagram that we looked at in the last podcast, okay, where we've got a certain number of particles, we've got the energy or the speed going on the x-axis here, is that there's an average here in the middle of the average speed of the molecules, but some of the molecules, okay, at this far right end, have a much greater speed, have a lot more kinetic energy, and so those are the particles that are going to evaporate. Okay, so you see there's this line here that says minimum energy needed to escape the surface, okay, in other words, to become a gas. So all of these particles that have this much kinetic energy, if they're at the surface, they can escape and evaporate. Okay, and over the course of time, you might get more energy into the system from sunlight or something like that, and that causes more evaporation. We've got a special name for liquids that evaporate really quickly. Those are called volatile liquids. We tend to associate the word volatile with something that's flammable or explosive. It doesn't necessarily have to be that. It sometimes is. When we think about some classic examples of volatile liquids, things like gasoline or alcohol, those are relatively volatile. They are flammable also, but volatile doesn't necessarily have to mean flammable. And then we get the term of vapor pressure. And vapor pressure is the pressure of the vapor above the liquid. So if we go back to our little flask diagram here, and you look right here, all of these gas molecules that are at the top of the flask, this flask is sealed off, all of these molecules, as they collide with the sides, they're creating pressure, okay? The force of their impact on the sides of that container is creating what we call vapor pressure, and that's the vapor, the gas, that's above the liquid gives us the vapor pressure. And then all of this relates also to the boiling point. And what boiling point is boiling point is when the vapor pressure, okay, the pressure of that gas above the liquid, equals the external pressure, okay? And so if the pressure outside is 1 atmosphere, if you're near sea level, then the boiling point of something like water is going to happen at 100 degrees, because at 100 degrees, then the vapor pressure of water is about 1 atmosphere, which is the same as the external pressure. In some of the videos that we watched earlier where it was a school in Colorado, they're about 8,500 feet up, and so their atmospheric pressure is only about 0.8 atmospheres, and so therefore water for them doesn't boil at the same temperature as it does for us here much lower down. So their water boils at maybe, say, 90 degrees Celsius, because the boiling point is where the vapor pressure inside equals the external pressure, and if the external pressure is lower, then you need less heat to get the vapor pressure up to that level. So some other phase changes. Condensation is going to be the reverse action of evaporation. Gas is going to turn back into liquid. Sublimation is when a solid turns directly into a gas, and a good example of that is if you think of dry ice. It doesn't turn into a liquid at any point, but that solid block of carbon dioxide turns into gaseous carbon dioxide. The opposite of sublimation is deposition. Okay, deposition is where a gas turns directly into a solid. Now, in the case of sublimation and deposition, depending on what the chemical is, you might have to not just change the temperature, but the pressure as well. Melting, we all know what melting is basically, but that's when a solid turns into a liquid. And then the last of these is freezing, when a liquid turns into a solid. And it's important to see that all of these things exist in pairs. If we go back to that very first slide, or the second slide that we had, you'll see that melting and freezing are paired together. Okay, melting solid to a liquid, freezing liquid to a solid. Condensation and vaporization related together. Sublimation and deposition are paired together then. So each of those things is going to be paired together. So, what does it take to then go from one phase to another? Well, basically, there are two things that are necessary. The first of these is that we have to have the energy to get the temperature up to the phase change point. So, let's say that we had an ice cube and we wanted to melt it, and the ice cube, the temperature was at negative 20 degrees Celsius. Well, we know that the melting point of water or ice is at 0 degrees Celsius. So, we have to put energy in just to get it to go from negative 20 up to 0. Okay, so that's the first thing. There's an equation that we use for that, and we'll talk about how to do that calculation. The second thing is that at every phase change, there's an energy required to basically change from phase to phase, or as we looked at in one of those first slides, okay, if we go back to the very first slide there, it's the barrier, the phase boundary. So there's an energy required to jump over that phase boundary then. Okay, so that's how we do those calculations. Okay, those are the two parts that are needed. So how do we actually do the math behind it? Okay, so we're going to start off with the heat of vaporization. Now, if you remember, look back at that first diagram. That's the boundary. That's the energy for the boundary between liquid and gas. So we're trying to turn a liquid into gas phase. That's vaporization. So the heat of vaporization is basically how much energy does it take to take 1 kilogram of the liquid and to vaporize it. Okay, and so for water, it's going to be 40.1 kilojoules per mole. Now, we haven't talked that much about moles yet, but we'll do that in the next section. Or, in terms that we've done it so far, 2.26 times 10 to the 6 joules per kilogram. Or, we could put that in conversion factor form. We could turn this number here into kilojoules, and that gives us 2,260 kilojoules, and that is equal to 1 kilogram. Okay, so to find that out then, to do a calculation, we would take our 2.5 kilograms, say that's just an example, I'm pulling that number out of thin air. So if I wanted to know how much energy it took to turn 2.5 kilograms of water into water vapor, into steam, I start with my given. Okay, put your little railroad tracks here for your conversion factors. And then we do what we normally do. We take our equality, and I'm going to put the 1 kilogram on the bottom. That way I can cancel kilograms out. Whoops. Okay, kilograms are going to cancel that way. And then the top half has to be the other half of that conversion factor. So kilogram on the bottom, kilojoules on top. We actually calculate that out. The kilograms are going to cancel. We're going to be left with units of kilojoules. You punch that into the calculator, 2.5 times 2260. Divide all that by 1. That gives you 5650 kilojoules. Okay, 5,650 kilojoules is going to be our answer. So pretty straightforward conversion factor type of problem. To do that step only requires 1 conversion factor. And remember that what we're doing there is that this is liquid into gas phase. Okay, same sort of thing is true for the other boundary, the boundary between solid and liquid. That's the heat of fusion. Okay, so if we had 10 moles of water and we wanted to convert that, we could use the other conversion factor there, the 6.01 kilojoules per mole. You'll note that this number is different than the heat of vaporization. It takes a lot more energy to turn liquid into gas than it does solid into liquid. The reason for that is, if you go back and think about kinetic theory, is that the molecules are moving a lot faster in gas phase. They're a lot further apart, so they require a whole lot more energy than they do just going from solid to liquid. Solid to liquid, they're not really that much further apart. They're just moving a little bit faster and can flow. So for the math for this one, take our given, 10 moles, okay? And then I'm going to take my 6.01 kilojoules. On the bottom is going to go the 1 mole, so that cancels. That comes from here, okay? And then that is going to give us, if we multiply that out, you're going to get 10 times 6.01, so you're going to get basically 60.1 kilojoules. Okay? So pretty straightforward calculations there. And we use that at every phase boundary. That's the calculation. It's a conversion factor. Okay, now the idea of phase boundaries here leads us to something called a heating curve. A heating curve is basically just a graph that shows how it changes over time. And so here's what's important to look at with these graphs. Okay, the slanted parts, the sloping parts, those are temperature changes. Okay, so negative 20 to 0 degrees. That's a temperature change. Certain amount of time, certain amount of temperature goes up. Then you'll notice that the very flat parts, okay, right here and right here, those are the freezing point and the boiling point. Those are the phase boundaries. So this is where solid turns into liquid. This is where liquid turns into gas. And what you'll notice is that they'll stay the same temperature for a long period of time, particularly for the boiling. It's a pretty lengthy amount of time here that's required, something like 15 minutes in this case, to go from all of it being water right here to basically all of it being gas here. Okay, that's a heating curve. You always know it's a heating curve if it's going up to the right. You'll know that it's a cooling curve if it's going down to the right. Okay, same basic principles though. Sloped parts are the temperature changes. Okay, flat parts are boiling and freezing point. Okay, we'll do a little worksheet activity to get you a little bit more familiar with that. To look at this a little bit more clearly, the temperature changes, those are the sloped parts. Okay, and then let me see if I actually drew in the other parts. I don't think I did. And then the other parts that we're going to look for, we'll just draw some quick arrows here. The flat parts then, okay, those are the phase boundaries. Okay, so that's melting, freezing, boiling, condensation. Remember,